The green things are positive, and you get a total counting value. Okay? Then if you add them together, that's the total amount of evidence. According to what, of course, or according to the system's experience. Okay? Be careful. This is just the definition of evidence. This is not how it is actually calculated. That's a different story. Okay? Here, let's go back to see what we have done. First, we define what is experience. We use experience to define truth value. Then we use truth value to define extension and intention. Then eventually we define one arbitrary statement. Given that experience, how much evidence you have, positive, negative for a given statement. Then finally, the last step, we use the amount of evidence to define truth value. What makes this system different is it's not only is multi-valued, it actually uses two numbers to represent the truth value. And many people say, oh, one number is already too complicated, you use two. Well, I have enough reason later I will show you. We use two numbers to represent a truth value. And both of them are real numbers between 0 and 1. The first number is called frequency. It should look very familiar. Is the proportion of positive evidence among all evidence. Like what I just said, okay, 80% support, 20% against. So frequency is 0.8. Okay? But be careful, this is not probability, because probability is relative frequency take limit, okay? I'm not taking limit. So it's just the current proportion of positive evidence among all evidence. And this evidence may come from extension, may come from intention, as I just defined. But still, this looks pretty natural. And the second thing, the second component is probably most unique in terms of the semantics of the system, is what I call confidence. Okay? This same word has been used by several different theories like statistics to mean slightly different things. So here, what I use is for, this W is the total amount of evidence divided by total amount of evidence plus 1. Y plus 1. Well, a raw story, okay, to make it short, actually it doesn't have to be plus 1. It can be plus, 2 or 3 or 1. But the intuition is we need a measurement to measure how much you know about that thing. Okay? Traditional theory, including probability theory and fuzzy logic, have a problem of cannot really say, I don't know. You see, probability 0.5 doesn't mean I don't know. Here, we have a mechanism to really say, I have absolutely no idea. That is, confidence equal to 0. Okay. You see, this W is how much kind of like evidence you have seen. If you haven't seen anything, confidence is 0. If you have seen one piece of knowledge or one piece of evidence for that statement, you see, it's 1 divided by 2, it's 0.5. You have C, 2 of them is 2 divided by 3 is 2/3. And then it will be 3 divided by 4, 4 divided by 5. It will never reach 1. So basically, my current interpretation in my publication is basically say, what this measures is what you know at the moment compared to what you will know in the next moment after you get one piece of new evidence. Okay? So the next moment, you will always know more than the current moment because you get one piece more. But if you already know 1 million, and that difference will be very small. 1 million plus 1. It is basically the same as 1 million. But 1 compared to 2, that's very different. So you see the intuitive meaning of this measurement is to measure how the system will be sensitive to new evidence. The more you already know, the less sensitive it will be. But there is always a chance for you to get new evidence. So mathematically speaking, this formula actually indicates why I call my system non-axiomatic logic. That is, no absolute truth. Everything can be modified. It will become harder and harder and harder and harder if you get more and more and more and more evidence. Okay. So graphically speaking, then now we can add a weight value to the link. This weight value is actually two numbers as a pair. Okay. So now we can summarize the semantics of NARS, which is very unique. I say this system has an experience-grounded semantics. In what sense? In the sense that everything, semantically speaking, is defined with respect to the system's experience. So you see the truth value of a statement is defined by what? By available evidence. It's about how much you know about this thing. It's not defined with respect to a fact, which is traditionally how truth is defined in flexible model theory. Okay? True means match the reality. Here, there's no such a thing as reality. What you have is your experience. You compare your belief with your experience to see to what degree they fit into each other. The same thing about meaning. Traditionally, in model theoretic semantics, the meaning of a word is its reference in a world. Okay? There's an object where this term or this symbol is just the name of that object, and that object gives this symbol its meaning. No, that's not what this system does. This system, the meaning is what is defined by nothing but the extension and intension, which I just defined, of a term, which is the experience relation between that term and the other terms. So what this bottle means depends on how much I know about it. Okay? It doesn't really determine by what it really is. So it sounds simple, but if you think about it, there are several important implications which make this semantics fundamentally different from the semantics which is dominating the current research. First, you see both truth value and meaning are subjective. They're not objective. It depends on which system you're taking. Second, both of them change over time because what? Because experience, by definition, extend over time. Okay? A system always gets new experience, and those experience, by definition, is going to change the meaning of the terms involved and the truth value of the statements involved. Okay? So objective or stable things, they're special cases. Changing things, subjective things, they are the norm. They're the normal situation. And also objective is relatively speaking, or stable belief, yeah, you can have them, but they're relatively speaking. So this is very, very important. That's again the foundation of everything else.
Okay.
Of the following.
So if I understand right, would it be fair to say that NARS uses procedural semantics rather than declarative one, where the meaning is based on the statements in which things occur, and the only kinds of statements your logic allows are specialization, generalization?
Not really. Well, it's related to later. I think I hope later I will explain the difference. But yes, there's some relation to what you said. Yes, but not exactly. Later we'll see it's not just specialization and generalization, and also not only procedural, and also it can be declarative. So that's how truth value are defined. Okay, how they're actually produced in the system. Of course, two sources. One is the input. Okay, the given, you have to, of course, provide the initial truth value. By you, I mean the user or the designer. Okay? But it will be produced according to the semantics. For example, we're experimenting using existing knowledge source like WordNet, hook it up with NARS, and provide information to NARS. WordNet doesn't come with truth value at all, it's just binary. Well, we can use some default value. Okay? Or if you already have statistics, we can convert the statistics into truth value in a certain way. Okay? So it can come from somewhere. Also, all the inference rules later we'll see is going to take premise which is true to a degree, which will generate the conclusion of course is also true to a degree. Where those numbers come from? Well, they come from a bunch of truth value functions designed by the designer, but it's designed according to the semantics I just introduced. So you see, again, remember in the following, when we talk about truth value in NARS, don't think about the reality. Think about what the system knows about that thing. Okay, that's what this is all about. So truth function design, actually, I also try to use probability theory in the first place because that's the most natural choice. But pretty soon I realized that it's not going to work. And so I use something else. Okay. The current approach is basically to treat the truth value in the system as an extension of Boolean values. Boolean value is just 0 and 1, right? We are going to treat 0 and 1 as an extreme case of the values I'm using, which is between 0 and 1. Okay, that's pretty natural. So we are going to start with Boolean value. Basically, we are going to study the boundary conditions first. So what if it's extreme, okay, 0 or 1? Then we are going to analyze the relationship graph between the premise and the conclusion according to the semantics I just introduced. Then we are going to build Boolean functions among the variables involved, data will see example. And finally, we are going to extend those Boolean values, Boolean functions into real number functions. You'll see that Boolean functions basically are built by 3 operators, right? Not, and or. And I'm using this very simple treatment to extend them from Boolean to real number. Okay, those functions have been used by many systems, but with different semantic interpretation and justification, which in ours we are doing the same, but we interpret them differently, which I'm not going to talk about in detail today. Okay, you can see my publication for details. But anyway, let's see concrete example. The simplest rule is the deduction rule. You see, if M is a type of P to a degree, S is a type of M to a degree, then S is a type of P to a degree. This is nothing but transitivity extended from binary to multi-valued, right? So according to this analyze, I built the following function, which is first Boolean, then extended into truth value according to the way I mentioned. Okay? I'm not going to explain the detail why that's the case, but intuitively speaking, think about it, it makes sense. So this is a concrete example. You see that this 1 and 0.9 are the default truth value. If you tell the system something without saying anything specific about how true it is, the current default value is 100% positive. Confidence is 0.9. Why 0.9? Why not 9.5? Well, it's more or less arbitrary, but not completely arbitrary. Okay? But anyway, that's the current default value if you don't say anything. Then if we believe, if you tell the system a bird is a type of animal to that degree, and the rabbit is a type of bird, the system will derive rabbit is a type of animal to a certain degree, you'll see that confidence level is lower than the premise, which again is pretty natural. Okay, if you have something derived from something given, the derived things are less reliable compared to the given things. But frequency is still 100% because there is no reason to doubt about the conclusion. All the positive evidence given are positive. So the graphical representation, I omitted the weight value. It's just kind of like, again, if you have a link from S to M, from S to M to P, then you build a new link from S to P. Actually, everything in my system can be explained as graph operation. Okay? Paul may like that, but later you will see the details are different from sigma and other graph-based representation. Okay? But there is such an interpretation. Deduction is trivial. Induction, this is probably the most interesting thing in this system. That's actually where it starts. Let's see this pattern. Again, another thing I don't have the time to talk about in detail is the formal language I use and the format of the rules I use are actually much closer to Aristotle's logic than first order predicate couplers. Okay? Which may sound wrong because most logic textbook will tell you otherwise. But I have a lot of evidence later I can show you if you want. Actually, Aristotle's logic is a better starting point if you want to do human reasoning, not mathematical theorem proof. Okay? Mathematical logic is not wrong, it's built for something else. So Aristotle logic, one important feature is it uses syllogistic reasoning tools. That is, two premises must share a common term, and the conclusion is a relationship between the other two. So we have already seen that in deduction, and here you see that's the same for induction. But induction, the difference is the direction of the inheritance. You see here you have a common term play a role of subject in both premises. And then what you're doing is you're building a new relationship between the two predicates. Some people may already say, oh, if that's the case, it should be symmetric. Yes, it actually is symmetric. Okay? So there is also a conclusion from P to S, which I'm just omitted in this description to make things simple. Okay? And before I talk about that, let's jump to the example. Swan is a type of bird, and swan can swim. Can you say bird can swim? Every textbook tells you, no, you cannot say that. That's a fallacy. That's true if you're using binary logic. You see, in this logic, what does it say? It just basically says that swan piece provide a piece of evidence for the conclusion that bird can swim. Because that conclusion is indeed valid as far as swan is concerned. Okay, I'm not talking about, once again, I'm not talking about all the birds in the world. I'm talking about the birds I know, which happen to be at the moment to be swan by itself. Okay?
So how does that change if you've got a few birds you know about that are swimmers?
Two more slides, you will see that. Okay? This is another important thing. For this conclusion, I only take the premise into account. Let's assume there is nothing else in the system. Okay? Of course, in reality, that's not true, but we will see that later. For this step, this truth value is built exactly according to the semantic I just introduced. Okay? If this is true, then this is one piece of evidence. If this is true, this is false, then this is one piece of negative evidence. The previous one is positive evidence. That's exactly what these two equations tell you. And then you convert that into truth-value relationship. That's what you get. So compared to deduction, you will see inductive conclusion is never very strong. If you do just one step of induction, the conclusion, by definition, the confidence will be lower than 0.5. Why 0.5? Is 1 divided by 2. Okay? W equal to 1. Then W divided by W plus 1 equal to 0.5. But in reality, because your premise is not perfect, what you get is less than one piece of idealized experience or evidence, so it will actually be less than 0.5.
Are you using 0.45 as an estimate because it's less than 0.5, or you're using something?
I'm using those functions to do the calculation, and the functions are built according to the semantics, built according to how truth value are defined. Okay, the detail of the function, you can read my paper, but that's the idea. I hope today you just get the idea will be enough. Okay, no way for us to talk about the detail of the functions. Semantically, we have abduction. Here is, again, you see the familiar pattern. Now the common term and the common property, or the common predicate of the two premises. Let's see the example. What you want to decide is whether Gao is a type of seabird. What you know is a property of seabird, that seabird tend to be able to swim. And Gao happen to have that property. By that alone, what can I say? You cannot say Gao's seabirds for sure, you cannot. But that gave you a piece of evidence to believe in. Okay? At the same time, for example, even though birds typically flies, a penguin does not fly, it gave you a piece of negative evidence for penguins to be taken to be birds. But it's not a final conclusion, it's just one piece of evidence.
Does it give you the reciprocal at the same degree?
Actually, if you see this, you will see that positive evidence are symmetric, but negative evidence are not. Yeah, we can talk about that later if you're interested. And then we answer that question. What if you have a whole bunch of evidence from different sources? Yeah, we merge them together. Okay? That's what this revision rule does. And the function of the revision rule, you will see that it's basically a way to handle, you can call it evidence accumulation, or you can call it contradiction resolution or something like that.